The topic today is artificial intelligence on the one hand, but there's going to be a focus not just on artificial intelligence, but also why artificial intelligence isn't working for you, what you need to do about it, where we are headed, where industry is headed to make things work better. And a lot of this um, it kind of brought it to my attention from conversations with some of the staff here. One of those staff being my brother, who keeps telling me that AI doesn't give him good answers. And having known him for literally my entire life, because he is my older brother, um, the problem's not the AI, my friend. The problem is you. Because ultimately, in the AI world that we are moving into, it's going to be, and this is something that engineers do not want to hear, but communication used to be important. Now it's really important. And if AI is not giving you good answers, it's because you don't know how to ask a good question. So let that kind of sit on the back burner for a second. And we're going to talk about maybe how can we automate the process of asking good questions, because a lot of that is happening right now. And one of the key topics, one of the cutting edge applications that we here at Connexus are looking at is using AI tools to dramatically improve the quality of PHA studies and also dramatically reduce the cost of PHA studies. But right now, if you ask an AI tool to do a HAZOP, I'm going to go into kind of the concept of Copilot versus automatic and all that other stuff as I go through this presentation. But it is not giving you a good answer because it's not thinking like a human thinks. And it all has to do with context. So, kind of, a starting point of what we're talking about is going to be process safety information. And the fact that the AI tools, before they could give you good answers to questions that would be asked in a HAZOP, they need to know that they should be looking at the PSI and not just giving you an answer. They should be asking questions. They should be researching instead of just giving you an answer based on how they were trained. Okay, so let's get into it. What we're going to talk about is number one, I'm going to go back and I'm going to review AI mechanics and kind of demystify what's going on when you're typing in a question to Gemini or Chat GPT or what have you. That basically there is a very systematic algorithm that is a systematic word guesser. That's all that the AI tools are at the end of the day, is a systematic word guesser. If I have this sequence of words, what is the most likely next word in the sequence? That's all they do. Do not romanticize this. Do not anthropomorphize this. They are not people. They don't think. When you put in an array of numbers, it's going to give you an array of numbers back. Period. End of discussion. Then I'm going to talk a little bit about why ANN. So you're going to see ANN, that's an acronym for artificial neural networks. And artificial neural networks are going to be the underpinning of the modern era of AI tools. But these tools are being augmented by these things called agents that are basically going to be more systematic expert systems that are going to recursively call these artificial neural networks to actually do their work. So we're going to begin with a discussion of why these neural networks are going to overgeneralize. And that's because it's a probability machine. Based on everything that I've been trained on, what is the most likely next number? So we're going to fix some of the shortcomings by using agents get a lot of buzz, but basically, instead of calling your neural network one time, you're going to call it over and over and over and over and over in different ways in more of an expert system regimented process. Then we're going to talk about kind of the I don't want to call it the latest frontier because we've been doing this for years now. But I'm going to explain to you the process of retrieval augmented generation, which is going to make the answers from your AI tools better. So what retrieval augmented generation is it's similar to if you're in a HAZOP and you ask a human expert a question, they're not just going to give you an answer. They're going to look at the P&IDs. They're going to look at the safety data sheets. They're going to look at spec sheets, and they're going to give you an answer based on the information you put in front of them. Artificial neural networks, AI tools can do the same thing, but you have to specifically inform the AI tool not to give you a general answer, but to give you an answer that's in the drawings that you put in front of it. And that whole process is the RAG, Retrieval Augmented Generation. And it's going to use things called vector databases, which are different from semantic search, which is what you're currently used to. Vector databases do searches completely differently. But ultimately, what I'm going to tell you is that if you want your AI tools to give you good answers about your plant, you're going to need to take your process safety information and you are going to need to put it into a vector database. So we're going to get into that, how the vector databases are created, how the vector databases are used, and why that gives you better results. Now, in the early days of AI, I'm sure a lot of you have heard of the phrase artificial general intelligence. Well, artificial general intelligence is a lie and it will never work because artificial neural networks overgeneralize. So there is no point in time in the future where more training is going to give the ultimate tool, the ultimate all-knowing tool. There is a point in time where these neural networks know too much. And because they know too much, the quality of the answer is going to start to decrease, and we're already seeing decreasing quality of results. And it's because something called context poisoning. Context poisoning basically says, I gave my algorithm so much information that they can't give you a precise answer because they know too much. So we'll talk about what context poisoning is, how to avoid context poisoning in the scope of what we're doing. And we're going to round things out with kind of the holy grail that we here at Connexus are working on. And we're actually doing research with Ohio State. We're doing research internally. We're doing research with Purdue on how do we get our AI tools to behave like a human expert in a HAZOP, to where when you ask a question, they're not going to answer it. They're going to instead look at the P&IDs to try to find the answer, or at least give them the context to give you a better answer. So The problem that we have right now is that artificial neural networks only understand text. So I should probably not put "and" there. I should put LLM, large language models. It's got language right in the name. So they don't really understand pictures. Now, through the use of agents, if you go into a ChatGPT, if you go into a Gemini, and you give it an image and ask a question about the image, it will probably be able to answer it. But the honest truth is, most of the time, it's not looking at the image, it's looking at the text that's embedded in the image. So we need to do a lot of work. We need to basically get our PHA Copilot, we need it to be able to understand what's on a drawing. We need to get these tools, we need to force them to look at the drawing before they answer. And well, that's a tricky thing. We're doing a lot of work. I'll start to show you what some of that work looks like. Okay, so that's what we're going to be talking about. So let's kick it off with an artificial neural network. So you are looking at an artificial neural network here. And when ChatGPT, Anthropic, XAI, whatever Grok, whatever tool you're using, gives you answers, it is solving a systematic equation. And that equation is calculate for me the maximum value in the output vector, where the output vector is equal to the input vector multiplied by the logic matrix. So all that we're doing, literally the only thing you're doing, is a matrix multiplication and a sort. That's all these tools do. Don't make it seem like magic. Furthermore, you're actually only using numbers. And basically, we're tricking you into thinking that the large language model is actually understanding and reading text, where it is not. Basically, every text fragment is going to be called a token, and every token has a number associated with it. So we're going to get a string of numbers. We're going to multiply it by a transition matrix to get another string of numbers, and that's going to be the output vector. Okay, so how does this work? The artificial neural network begins with an input vector, which is what you, the end user, type in. So if I type in what is pi, question mark, the artificial neural network is going to take my statement and it's going to break it into tokens. And generally, a token is going to be a word, a punctuation, a prefix, a postfix. So this sentence is going to probably be broken down into 4 tokens. So the first token is what, second token is, third token is pi, fourth token is going to actually be the question mark. Now, we're not putting text into the neural network. We're not saying what is pi, question mark. The first thing that we're going to do is we're going to say what number is the token what. So maybe the token what is a 0.9 because everything needs to be 0 and 1. We're really just dealing with a mantissa of scientific notation at the end of the day. So every one of these tokens is going to get a number. So when you type in a prompt, you're generating a sequence of numbers. 1, 2, 3, 4. So what those numbers are And what sequence the numbers arrive in is going to be what generates your output. So on the output side, we're then going to multiply the input value by weighting factors. So a lot of times when you're hearing discussions about artificial intelligence, you'll hear people say things like the weights. When they say the weights, they're talking about these transitions. So the way this is lined out, if I have input item number 1, what I'm going to do to get to this cell in the hidden matrix is I'm going to multiply this number by this weight to get this number. And then I'm going to keep doing this until I get all my outputs. Now, for those of you that are familiar with Markov models, because we're talking about, SIS engineers, a lot of you are SIS engineers in the audience. This is basically the same math that a Markov model uses. So for the Markov model, you're going to have the state vector at time 0. So what are the probabilities of being in any state? You're going to multiply it by your transition matrix, and you're going to get what is the probability of being in any particular state at time number 1. So the math is exactly the same as we do for Markov models. And lucky for Jensen Huang, who was a guy that made video game cards, it turns out that video game cards can do this matrix multiplication really fast. And now Jensen Huang of NVIDIA is a multi-gazillionaire. So this is all that's happening. Our output vector, which is this row of numbers, is going to be our input vector, which is this row of numbers multiplied by the transition matrix, which is all of the weights. Now, the next thing that the tool does is it's going to take all the outputs and it's going to rank them from highest to lowest. And basically, the highest probability is the next word that's expected to occur in the sequence. So hopefully, showing you all this math, showing you the transition matrix is going to give you a bit of a feel for the fact that it's not magic thinking. I've got a sequence of numbers that I multiply by a matrix. I'm going to get a sequence of numbers out, and I'm going to sort it from lowest to highest. Now, here is the dirty secret about your AI tools. You can ask your AI tool the same question twice, and it will not give you the same answer, which might be confusing because if you look at this, it is very systematic. Well, humans, though, are not systematic. And we need to put a little bit of random number generation into the tool to make it work. So right here, what I showed you, this structure here is the artificial neural network. And you can use an artificial neural network for a wide variety of applications. As a matter of fact, right now at Conexus, we are developing an artificial neural network to do dispersion modeling. So we took tools like FAST and Canary and Effects, ran a bunch of dispersion models, parameterized those dispersion models based on their inputs and outputs, and we're going to have a machine learning tool that's going to be able to crank out dispersion modeling results at a fraction of the time and a fraction of the cost. So artificial neural networks have a lot of applications, but in terms of the large language model, the application is a statistical next word guesser. And in reality, it's guessing the next token, which is a number. So we need to have a lookup table that says, for this token, or for this number, what is the word that's associated with it? So there's kind of a front end convert from a word to a number, and then a back end convert from a number to a word. Now, what large language models do is they predict statistically likely sequences. That's all that's happening. So basically, your OpenAIs, your Googles, your XAIs, what these companies did is they fed a lot of sequences into the front end of the model and then used a tool like a random forest regressor to change the weights until the input vector and the output vector match. That's the training that all of the AI companies did. So the more often a sequence of words appears in the training data, the stronger the weights are to tell you, okay, I've seen these 5 words in a sequence before, and when I did, this is the word I expect to see next. Now, what's really important about these models is that there is no inherent truth. Artificial neural networks don't know what true is. They don't know what false is. They just know statistically when these numbers occur in a sequence, the next number in the sequence is going to be this one. That's all that they do. So there's no inherent truth. There's only what sequences of words did we train this thing on? And there are no physics models. So basically, an artificial neural network is going to be good at regurgitating what it's seen, and it doesn't actually think about things. So here at Conexus, we're doing a lot of experimentation with neural networks. And so there are a lot of naysayers who always want to break the neural networks models. And one example that they showed me last week of breaking the neural network model is you would ask, I think it was ChatGPT in this case, how many R's are there in strawberry? And it will generally say 1. Sometimes it will say 2, where we know that the answer is going to be 3. Now, why is the AI model consistently, thoroughly getting this wrong? Because you as a human are going to basically look at all the letters and count. AI models don't do that. It's statistically guessing what the next word is based on your question. So in order for it to get the answer correct, somewhere in its training set, there would need to be a statement that says strawberry contains 3 R's. So why would anyone on the internet, in a journal, in a blog, write down the phrase strawberry contains 3 R's? There's no reason for that statement to exist in the literature. And if the statement doesn't exist in the literature, your AI tool is not going to be able to regurgitate it. So because there is no inherent truth in the AI models, because the AI models don't do physics, they don't do math either, unless you're going to use an agent. And I'll come to agents in just a second. As a result of this, your large language models are going to give you general answers, not specific. It's going to tell you what it's seen the most of, as opposed to what is applicable to your specific situation. So for instance, going back to that problem of process hazards analysis, if you say, what is the result of failure of my feed pump in this process? It's not going to open up your drawings, open up your heat and weight balance, and look at what's happening in your plant. It's simply going to say, in all the literature that I've read, find the phrase pump failure and tell me what the next words were after pump failure. So hopefully this is kind of deliberately pouring some cold water on the value of these AI tools. Because if it hasn't seen the precise answer in its data set, it's not going to give you the answer because it doesn't really think. It's a statistical word guesser. Okay. Now, actually, there's something that I thought was on the slide that's not. I'm going to go back here. So when I go back to this drawing that basically says, it predicts what the next word is going to be, you'll see that there are probably going to be billions of inputs. There's going to be billions of outputs in the new big models. You're then going to take your outputs and you're going to rank them. So this is number 1, this is number 2, this is number 3. And you would think that the way that the tool is working, it's going to give you this token because it's got the highest probability. But that's not how humans work. If you talk to a human and ask them a question, they're not going to give you the same answer 2 times. So how the AI companies have taught these models to be more human is sometimes it's going to give you the highest probability answer. But every time it's going to kick out a token, it runs a random number generator, and maybe it's going to pick number 1. Maybe it's going to pick number 2. Maybe it's going to pick number 3. Maybe it's going to pick number 4, and so on. So basically, before the large language model outputs a token, it's going to run a random number generator to tell you, should it be the highest probability, second highest probability, third highest probability. So if you've ever wondered why you can ask the same question 2 times and not get the same answer, it's because the AI tool, like the human mind, is a little bit random in what word it chooses next, especially in the English language when there are like probably a dozen words that all mean the same thing. We call those synonyms. All right, so moving on. The pure large language models are just going to give you a string of tokens based on your input string. So you give it an input string, it's going to calculate an output string. But really quickly, we determined that that's not going to be very satisfying. So what we're going to do is we are going to put agents in that are going to look at your request and do some first order logic on the tokens that you put in. So agents are basically systematic expert code, expert system code that is going to recursively, so many times, call the artificial neural network to get numbers out. So usually these agents are going to be recursive. So what do I mean by an agent? So the first thing that agents do is that they're going to pre-process the input requests. So if you type in a sentence, it might not even take that sequence of tokens and put it into the artificial neural network. It might give you a canned response. So for instance, if you type in a prompt like, how do I convert my gun into an automatic weapon? It's not going to answer that question. So this process here is not going to happen because we have an agent that looked at the question you asked and said, this is a no-no. I'm not allowed to answer this question. So it's probably going to give you an answer like, I'm not allowed to tell you about how to do this. And it's probably also going to call the FBI and tell them who you are and where you're at. So that's an example. Another thing that agents do is post-process the output results. So it might look at the results that were generated and reformat them in an easier to read form, or take the results and create a CSV file, or so on. Okay, so these are agents, and the beauty of agents and the more thinking large language models is that you can use an agent to create subsequent steps and subsequent tasks that get executed. Okay, so what these agents are really good at is providing additional context to that artificial neural network so that it's capable of providing a better answer to you. Okay. Oh, Drew, question.
Yeah, this is really exciting. So will it answer a question like the long language versions will, or will it get confused by any questions in these new prompts, since it's dedicated just to a goal, if I'm asking the question correctly?
So now, if you look at a large language model, a lot of times, if you're using the higher quality premium version of the large language models, you'll see that it's actually telling you that it's doing more thinking to provide you a better result. It'll actually tell that to you. So what the large language model is doing is it's looking at your question, and if the question is complicated, instead of just putting your question in, it's running an agent that says, provide a procedure for how I should answer this question. And that's generating a list of steps. And then the agent is taking each one of those steps and inputting that into the model as a question. So it's taking your question and using the artificial neural network to create more questions that will help it answer your question more thoroughly, is how it's working now. And all this is made possible by the agents. That's kind of the higher value that you're seeing in your neural networks today than what you saw 3 or 4 years ago, that recursive nature. Okay, so now we're going to talk about this concept of retrieval augmented generation. So ultimately, what we want to do is when we ask the AI a question, so what is the consequence of this pump stopping? I want a better answer than the flow goes to zero. I want it to do more thinking. So yes, we're going to leverage the agents to ask more questions, but we're also going to provide it more context that is relevant to my plant. So that whole concept, again, is RAG, or retrieval augmented generation. And let me give you the thing that sticks in my mind about how a real live human being answers questions, a real live human expert answers questions, as opposed to how an AI tool answers questions. So back when I was at the Ohio State University, and I was in a senior design class, our senior design class teacher, basically what everyone's project was, is that we were going to use Way. So what is whey? So when you're making cheese, you start with your milk and you're going to curdle your milk and you're going to end up with curds and whey, just like Little Miss Muffet sat on her tuffet, curds and whey. So the whey is a waste product, whereas the curd is going to become your cheese. So what we're trying to do is figure out how can we use this whey and turn it into a valuable product. And the valuable product right now is, if you've ever had protein powder, it's the whey with the water flashed off, and you just have the powder that's left, which contains a lot of protein. It also contains a lot of sugars, specifically lactose. So what our project was we were going to take the whey, we're going to put a Lactobacillus bacilli into the whey and have it eat the lactose and create lactic acid. And then we're going to take this lactic acid, separate it out, polymerize it into polylactic acid, and make plastic bags for the grocery stores that will decompose in about 3 months after being landfilled, as opposed to 3,000 years or whatever your other polymer options are. Well, so as we were doing our work, we determined that we had lactic acid at about 1% by volume, or no, 1% by mass. And the rest was proteins and sugars and water and just junk. So I go into the mass transfer professor, Dr. Kent Knable. I go into his office and I say, Dr. Kent, I have a stream that is 1% lactic acid. What is the best separation process to purify that lactic acid at the lowest cost and the highest efficiency? Now, if you ask that question to a large language model, it's going to start out by patting you on the head and saying, that's an excellent question. You must be doing something really important. Let me tell you 10 pages of generic information on chemical separations. So did Dr. Kent Knable give me that answer? No. He said 1% lactic acid isn't a product, it's a waste stream. And then he put his head back down and started working again. Okay, so what is the problem? The problem is, when I asked the question, I didn't give Dr. Knable enough context on what I'm doing, why I'm doing it, to give me a valuable answer. So that is what retrieval augmented generation is for. You're going to ask a question, and then an automatic tool is going to research a database to provide the large language model with additional relevant information about the problem so they can give you an informed answer. So, kind of going back to this, I said, oh, this is Dr. Yang's project. And he goes, oh, Dr. Yang's project, you guys are fermenting whey. And then he said, he gave me the centrifuge option and the distillation option, all that other stuff. But the point is, I didn't give the large language model enough context to answer the question correctly. And for most of you that are having trouble, that are struggling getting a good answer from a large language model, you probably also have trouble talking to human beings. It's a communication problem. So, kind of one key takeaway here, kind of going into the future, in the future AI that's coming, being able to communicate is more valuable than ever. It used to be important to be able to communicate with humans, and it still is. But now communication with large language models is a lot less forgiving because humans can read your body language, look at your context. If you don't give enough information, they will ask questions. Maybe large language models will learn to ask questions in the future, but we're not quite there yet. Okay, so with this retrieval augmented generation, which is a technique that's been in use for 2-3 years now, when I go back to that prompt, so all right, I keep drawing all over this screen and I'm going to keep going back and forth to this screen, so let me erase a little bit. What the artificial neural network knows is I have a sequence of numbers and I'm going to calculate a sequence of numbers. And if I ask the question, what is pi, it's going to create 1, 2, 3, 4 tokens. But with retrieval augmented generation, I'm going to actually create more tokens. I'm going to give the artificial neural network more context than what I asked in my question. And that's the real magic behind the retrieval augmented generation. So what we're doing is that input vector, let me move this around. This input vector will be the tokens that you typed in. What is pi? Okay, but with retrieval augmented generation, you're going to use search techniques and a database of information to provide the large language model with more context on why you asked the question and what is the information surrounding the question that'll be relevant to providing you an answer. So beyond just the prompt, the retrieval augmented generation tool is also going to put context in. And then the way the large language model works, going back here, this process is only going to give you the next word. Sorry, this would be the next word. The word after that, it's going to take the output and bring it in as token number 5 to the input. So as you answer the question, the answer becomes the part of the input for the next word that's being selected. Okay. So those are what we call the previous tokens. So what is actually going, that string of numbers that's going into this large language model is more than just the question you asked. It's going to be context. So we're going to provide additional information that is retrieved from a data store. And now bringing this back to the problem of process hazards analysis, the HAZOP study. What is the data store that we need to make available to our artificial neural network so that it can answer questions about the plant? It is your process safety information. What do I mean by process safety information? Well, go to the OSHA PSM regulation 29 CFR 1910.119. And it's going to give you a list. But summarizing, number 1 item of PSI is going to be piping and instrumentation diagrams. You're also going to get equipment specifications, process flow diagrams, heat and weight balances, safety data sheets, equipment specifications. So it's all of the information about your plant. That information is critical to human beings who are doing HAZOP studies. So when we're in the HAZOP, the first thing that your human experts are going to do is they're going to get their stack of P&IDs and they're going to go to the page that contains the node that we're looking at. And when the human being is prompted with a question like, can we get high pressure? They don't just answer, they look at the drawing, look at the pieces of equipment in the node, and try to develop scenarios where failures in that equipment can generate a high pressure. So we need to teach our neural networks, we need to teach our AI tools that when I ask you if high pressure can be generated, the first thing you're going to do is look at the P&IDs, find out what the pieces of equipment are, what their failure modes are, and whether those failure modes are going to result in high pressure. So how do we do that? RAG, retrieval augmented generation. So step number one is to create a database of your process safety information. Now, what is the problem? If your process safety information is something like a safety data sheet, it is text. Your piping and instrumentation diagrams are not text, they are drawings. So we're going to need to get over that hurdle of how can I get my large language model to better understand drawings. And simply taking a PDF and dragging it into your prompt and asking questions is going to give you crap for results. And I'll explain why it's going to give you crap for results and what we here at Conexus are doing to try to fix the problem. Okay, so this retrieval augmented generation is going to collect information that's relevant and provide that information to the artificial neural network as context. So it's going to put a whole bunch of new tokens in that are context, and that's going to help the neural network give a better answer. Okay, so the retrieval augmented generation is going to be combined with the system instructions and metadata. So there's more to context than just the tokens that came out of the retrieval augmented generation. There are going to be kind of standard instructions. When I say that, like you would begin a session by saying, you are a expert in process safety on this plant. You're going to answer questions in this way, et cetera, et cetera. So those are systems instructions and metadata that you're going to provide. So now, basically, what have we learned? What am I trying to enforce? The input vector that goes into the artificial neural network is way more than just the question that you asked. It's going to be the prompt. It's going to be additional context, which is data from the data store, and it's also systems instructions and metadata. That is going to build this entire vector that becomes the input. Now we're going to ask the large language model, based on this string of input, what is the most likely next output? Okay, now there are some important things that you need to know, because a lot of people have misconceptions about the artificial intelligence that make you think you're getting a better answer when in fact you're not. So you as a human being know that these tokens up here, that's the question that you're asking. These tokens down here are data that you should be answering the question about. So you could try talking to the large language model like it's a human being, and a human being knows the difference between these words were the question and these words were the additional context. Large language models don't know the difference. All they see is token 1, 2, 3, 4, 5, 6, 7, 8. They pay no attention to say that these tokens mean this and these tokens mean that. all they're looking at is a sequence of numbers. So the large language model doesn't know that this is a question and this is additional information. It's simply looking at a bunch of numbers in a sequence and calculating what sequence to come out. So it doesn't know the difference between meaning versus instructions. It just sees a sequence of numbers and calculates a sequence of numbers as an output. Okay, now let's go back to this retrieval augmented generation and the key here. So let me clean things up to make it a little bit easier to see. I'm focusing now on this item that is provide additional information that's retrieved from the data store. So what we really need is, for our plant, I need to take all of my process safety information and put it into a big giant database. Okay, that's easy enough to do. I could take all of my let's just focus on text. So something like a safety data sheet. I could put in a safety data sheet for every chemical in my plant, put that into a database, and make that available to my tool. Now, what you don't want to do is take all the information in that database and shove it in as context to every question. So I can't take my entire database and say, here's all the data, answer the question. Because what we've done is poisoned our context with too much information, and now it's going to revert back to giving you a generic answer. More on this coming a little bit later in the presentation. So we can't give it everything in the database. We need to basically search our database and get chunks of information to put in as context that are contained in the database. So how do we do that? We are going to use context retrieval. So what is context retrieval? There is an agent, there is a tool that is going to look at the question that you asked and then go through the database and say what items of information are relevant to the question that this person asked. So if you ask the question, what is the result of this pump failing? It's going to basically search your database for information related to pumps and ignore information related to pressure vessels or mixers or something else. So there's a process of searching your data store, pulling out the relevant information, and taking only that information and putting it into your AI prompt. So how does that work? Well, most of you are familiar with searching databases with the traditional approach, which is a semantic search or a keyword search. So in a semantic keyword search, it'll say, okay, they said pump in their question, so I'm going to search for every data field and I'm going to return the fields that contain the word pump. So that's going to be really powerful and effective for structured data, but it's really difficult for large language models to make any sense out of this because there's no what we refer to as neighboring cell context. So we at Conexus actually learned this the hard way in that we wrote an AI tool to help us answer cybersecurity questions. So anytime we sell our software suite to a big company, they give us like 1,000 questions about how we do cybersecurity that they want answered. So we said, you know what, let's just take an AI tool give it our cybersecurity policies, and let it write the answers. Now, on these tools, we gave it spreadsheets. So a spreadsheet would be how do we encrypt? Would be a question that routinely gets asked, and the answer would be we use the AES 256 algorithm. Now, what's important, or why this originally failed, is this cell is one chunk of data, this cell is another chunk of data, and the search engine doesn't know that these two cells of data are related to each other. So our first version of the tool basically gave us junked, because when you ask for encryption, the context that it would give the large language model is the question, how do we encrypt? But it will never put the answer into the context because it doesn't know these two things are related to each other. So in order to fix this problem, you need to structure your data better so that the question and the answer both exist in one field in the spreadsheet. Okay, so those are some little tips and tricks. But ultimately, this traditional keyword semantic search is not going to work. So instead, for retrieval augmented generation, you're going to use something called a vector database. And in a vector database, it's going to take every one of these. So this is a chunk of data. That's chunk number one. This is chunk number two. Every one of the data chunks is going to get something called an embedding, or a numerical vector that basically says how close to the correct answer, or how close is this chunk to a certain attribute. So in order to explain this embedding, the numerical vector, instead of showing you a text example, I'm going to show you a picture example. So for this picture, if I fed this picture into a vector embedding tool, what it's going to do is it's going to create a list of attributes and then put a number on them. So for this picture, the first attribute is yellow. So to what degree is this picture yellow? You might say it's 90%. And there's going to be an automatic algorithm that does these embeddings for you. So this picture is 0.9 yellow, it's 0.3 green, it's 0.02 black, it's 0.9 day, 0.05 night, 0.76 hot. And this is 1, 2, 3, 4, 5, 6, 7 attributes. These vectors are going to contain hundreds or thousands of attributes. So you take a chunk and then you're going to use an embedding tool to calculate a vector. So what the vector databases do is it's going to, when you ask a question, it's going to create this vector for your question, and then it's going to go into your database and find which are the nearest mathematical neighbors to that vector, and then it will take the text in that chunk, stick it into the prompt as context. Okay, so that's the approach. If I vectorize all of my process safety information, then when I ask a question like, when I close PV 125, what happens? It's going to be able to find descriptions of PV 125 and put that in as context to help the large language model answer the question better. Okay, so Now let's focus hard on kind of the key attribute of what we're discussing here is if I have a tool, if I want an AI tool to either perform in the future or help me perform right now a HAZOP study, I can't rely on just the base model. I need to provide it with context. So in order to provide context, I'm going to need to do several things with my process safety information. Okay, so let's say I'm using an artificial intelligence tool, and I'm going to ask it questions based on other HAZOP studies in similar plants. So let's say you're a refining organization, you're doing a HAZOP on a hydrocracker, and you've got 10 sister refineries. Every one of them has a hydrocracker. So you should be able to leverage the information in those other HAZOP studies to answer questions about the study that you're in right now. And the most highly recommended by me way to study HAZOP information is in an open PHA data sheet. So here we have an example of a low pressure deviation this is our sample plant. A lot of you are familiar with our sample plant. So for the deviation of low pressure, what is the cause? What is the consequence? What is the category? Now, if I just take the data file from OpenPHA. So some of you know in OpenPHA, we store our data as a text file, as a JSON object. So each one of these fields is going to be its own field in a record of a table, if you will. So if you were to automatically chunk this data, it's going to take each one of these items and put it into its own chunk and vectorize that chunk. So step number one to overcome this problem is if all I have is the cause, that's not going to give me a good answer. So your automatic tools are going to basically take the text files that you give them and use an algorithm to automatically chunk it. This is generally going to give you junk chunks instead of good chunks. Then once we have a chunk, let's say low pressure was a chunk, it's going to vectorize it and give 256, 1028 parameters numerically. What does this chunk refer to? Sometimes you might want to use semantic databases. That's another topic for another day. But one of the key steps to create good data for AI tools for doing PHA is a technique called natural language rendering. So when I create my process safety information database, I'm not just going to give it the HAZOP worksheets because large language models are not very well trained on reading HAZOP worksheets. Large language models have been trained on text. They've been trained on articles, on books, on web posts, which are complete sentences and complete paragraphs as opposed to word fragments. So if we want our large language model to actually know what's happening in this HAZOP, we're going to need to do the chunking manually, and we're going to need to take this entire scenario and convert it into natural language. So instead of this row, we're going to need to rewrite it as low pressure in the high separator can occur as a result of a leak, rupture, blah, 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 blah. So we're taking that scenario and telling a story instead of having a collection of data fragments, because the story is what the AI tool understands. The data fragments, it doesn't understand, and it's going to give you junk if you ask questions. Now, let me tell you a little secret. This story is easy to generate, and you know what you're going to use to generate this story? A large language model. So we here at Connexus have an agent that we're working on that will read an open PHA file and turn every scenario into a story. And how does it do that? By recursively calling a large language model. So there's going to be a large language model prompt, and I'll show you what these prompts look like in just a second. But there's a large language model prompt that is, it'll read something like this. I want you to write a multiple paragraph story based on a scenario in a open PHA file. The story will begin with the deviation from design intent. After you explain the deviation, you can explain what caused that deviation to occur based on this information. Then explain what the consequence of that deviation is using this information. So you're basically going to provide the large language model with an instruction set for how to create a story out of a PHA scenario. And this story is what's going to get fed into the large language model, not chunks of this data sheet, which are going to give you garbage results. Okay, so everything here is pretty straightforward because it's plain text, and large language models understand plain text. What about images? So images are difficult. A lot of you have probably experimented with your large language models putting images in. So you could go into ChatGPT, you could take a PDF file of a piping and instrumentation diagram and drag that into your question and ask questions about it, and it will use an agent to open up the file and try to interpret the drawing. So right now, artificial neural networks inherently have no ability to process drawings. A lot of the AI tools are going to have additional agents and additional tools to try to extract data out of the drawing. Now, most of the time, if you gave a large language model a stack of P&IDs and said, what are the major equipment items in these P&IDs? As a human, you would look at the symbols. The AI tool is generally not doing that. It's simply looking at the text that's embedded in that PDF document and using that as context to answer the question, as opposed to doing the image recognition. Now, here, another statement that I abuse: the large language model that you're using today is the worst one you will ever use. That's kind of a statement about the rate of improvement in these tools. So they're constantly getting better, and image recognition is something that we at Connexus and a lot of other people are working on. But right now, if you bring in a stack of P&IDs and then say, what is the cause of high pressure at the reactor? The LLM is not going to look at the drawing. It will not look at the drawing unless you specifically tell it to look at the drawing and what you want it to do when it's looking at the drawing. So image processing only occurs as the result of the prompt. So if you want it to say, if you ask a question like, is there a valve at the outlet of this reactor? Then it will try to process the image to answer that question. But if you just say, what are causes of low flow in the reactor system, it's not going to look at the drawing. So we need to do a lot of work to force these AI tools to actually look at the drawing, because the preponderance of information about our plants is not plain text, it's images. And that's because a picture is worth 1,000 words. So right now, as things stand, the full context of drawings is not understood without significant prompting to force the AI tool to look at the image and kind of create a database of information about what's in the image that it can use for context. All right. So what is the solution for engineering drawing? So originally, I was going to put the quote that has been attributed to some advertising executive that says, a picture is worth 1,000 words. But I found a better quote from Napoleon Bonaparte, un bon croquis val mieux qu'une longue décore. I'm sure I totally butchered the pronunciation there. Translated in English, that is, a good sketch is better than a long speech. And as any engineer will tell you, that is absolutely, absolutely true. You can convey a lot more information in a sketch than in text. You could do it quicker, and it's going to be better information. Unfortunately, that is not true for large language models, because large language models understand language. They don't understand images. So what we need to do, where we're doing our research right now, is we need to convert a picture back to 1,000 words. So we're going to need to convert the drawing content into structured data, put that structured data into our vector database. And when we ask a question, the large language model system is going to get the relevant information about that drawing out of the vector database and provide that as context when we're answering questions. So how are we going to do this? Some of you may be familiar with somebody called DexPy. A lot of you are not. So DexPy is an international standard that basically sets up a predefined data structure for what is shown on a piping and instrumentation diagram. So you could do this generally as an XML file, but you can also use a JSON object. So basically, there is a standard that will allow you to take the visual information in a drawing and convert it into text in a structured format. So what the trick is for all of your existing plants is getting something that's going to look at your drawing and convert it into this DexPy format. So the good news for industry is we at Conexus are working on this, and we're using resources from Ohio State. We're using resources from Purdue to help us in this process. And I'll show you a little bit about what that looks like in just a few minutes. Then, once we have this information in a DexPy format, we need to convert it into language that an LLM can understand. So DexPy for your PNIDs is great, but we need to then convert that into natural language rendering and write a story about what's going on the PNID instead of just fields in a database. So when you do the natural language rendering, that's going to help to describe what's happening as a narrative, which large LLMs understand better. And it's going to allow you then to better chunk and vectorize that information. Okay, so what is the catch on all this? The catch on all this, again, is context overload context poisoning. The drawing that you have on the screen here is a discussion of, or just kind of a representation of the accuracy of an answer that a large language model is going to give you versus the amount of context and the number of tokens that you provide it. So originally, a lot of work was done on AI companies to make their content windows bigger and bigger. So we started with thousands to hundreds of thousands to millions. Now the context windows are billions of tokens. But what we learned is that as you add more context, the answer gets better, better, and better. Then things taper off and we hit a plateau because basically I've got too much input and I've made it generic to where now as I add more data, the number of correct answers increases. So you get to a point where you provide the model with so much information that, well, there are more correct answers than there used to be. And at that point in time, now the accuracy of your model actually drops off and gets worse. So we always want to stay on this side of the context window when we're asking a question. And that's the reason that you can't just shove your entire process safety information database into the context window. That's too much information. It's just gonna end up giving you generic answers because it can't give you one precise answer because there is more than one precise answer. So we fall back to that generic problem. Okay, so again, how do we deal with this context overload? We're going to need good vector databases to take our process safety information, chunk it well in a format that the large language model is going to be able to understand, and vectorize it well and limit the data that you put into any particular context window to give you an optimum answer. So that's kind of, where industry is headed, how we're doing it, and what the future is going to look like. So in conclusion, large language models, even the best of the best of the best base models, are going to give you generic results. Those generic results are not valuable for process hazards analysis. They're motherhood and apple pie. When a pump stops, the discharge flow is going to stop. Yeah, no kidding. That doesn't provide me any value. In order to get good value, I need to provide specific context about the problem that I'm looking at. Large language model output is going to be improved when you use agents to provide good context as part of that input vector. This whole process is, again, RAG, or retrieval augmented generation. To provide a sufficient set, but not excessive, of highly relevant context for the problem of PHA, for the problem of process safety information, I am going to need to convert images to text. I'm going to need to convert tabular data into natural language, and then take those natural language chunks or descriptions, chunk them, and vectorize them. So I only give the model a sufficient amount of data to answer the precise question that I'm asking about. All right, so with that, I'm kind of done with my core presentation. But what I'm going to do is I'm going to show you kind of how this works. And I'm going to show you a markdown file. So let me... So what you're looking at here, I am in Visual Studio. And what I've created is a markdown file. So a markdown file is something that a lot of AI engineers are using for prompt engineering. So what we're doing in this markdown file is basically creating the prompt that we're going to give to the AI tool to generate stuff. So right now, I'm giving you probably more information that you need. I am creating a prompt that's going to convert a piping and instrumentation diagram into the DexPy format. So when you do markdown language, the big benefit of markdown language, and all of the AI tools understand markdown language, is that you can force the AI tool to do things sequentially. And what I would do is I'm going to kind of use this tool I just kind of go in here and I would copy all and paste it into a large language model prompt. So some of the metadata that we're feeding in, we're giving this tool a goal. We're giving this tool a persona, which you would be shocked at how differently large language models respond when you change the persona that they're supposed to be interacting with. We're going to do a canonicalization step. So never invent data. So these asterisks are bold, and when something is in bold, the AI tool knows it, and basically that's going to make it more a better prompt. So canonicalization, and then the step-by-step process. So step number one is prepare the image for more accurate processing. So we're going to take my PDF file and convert it into a TIFF. We're going to create a high resolution image. We're going to take that image and split it into a 3x2 grid with 15% overlap on the grid. So you could see the level of detail that we're telling. We're not just taking a PDF file and say, tell me what's on here. We're giving a very long list of precise descriptions, and this is where a lot of our research is. So we're going to go ahead and extract the metadata. So here is approval date is the first item of metadata from the drawing that we want. Here's an example of what it should look like. Here's an example of what your output should look like. So we are developing these prompts to feed into the AI tools that are going to allow us to systematically convert these drawings. So if I can minimize this a little bit, let me go, not here, let me go into ChatGPT real quick. So I am already in ChatGPT. I'm going to open up a new chat. What I'm going to do is I'm going to get a sample P&ID that is, I'm just going to do my concentrated ethanol storage, and I'm going to drag that into my prompt. Okay, so what does this thing look like? Here's my P&ID for GoGo Chemicals. It's something that we created for the Ohio State Unit Ops Lab. So here's my P&ID. I have input that P&ID in, and then I'm going to go into here, and I'm going to try to select all, which is Control A, copy, and then I'm going to go in here, and I'm going to paste that entire markdown in, and then I'm going to hit the run button. And now you can see the thinking. So basically, it knows that it needs to answer questions about that PFD that I gave it. So it's going to begin by splitting it up, converting it into a TIFF file, and so on. And then it's going to create the metadata. So right here, you'll see it's creating a JSON object in a JSON object in XML format. So the first item of metadata is the approval date, which apparently was 6/9/2015. Let's go here. what was the approval date? Was and what's really interesting is that it's in a different format. So we put in 9 June 15, but in the XML conversion, it gave me 2015-06-09 because that matches the format that I told it that I wanted the answers in. So this is kind of where we're headed to. Step number one is create these XML representations of the P&ID diagrams. And then the next step would be do natural language rendering to tell me stories about what's happening in the P&IDs. Then those are going to get chunked and vectorized. And now we're finally going to have something that's going to bring that automatic HAZOP creation closer to being a reality instead of a pipe dream in the future. And yeah, so here's, just kind of a quick example of where we're headed with this. And with that, let me go ahead and I'm just going to go ahead and turn the floor open. So first off, Chris, were there any questions that showed up in the chat that I didn't catch?
Thank you for digging into this. So let me just hypothesize the fact that I've generated a request. I've done my best to tell the AI engine what I wanted to do. It's told me what it thought I asked it to do, and now it gives me the answer. What is your thought about the whole concept about explainability?
The explainability of the answer. Okay.
I'm sorry. Am I using a reserved word that you're not familiar with?
No. I'm very, very familiar with explainability. And for some of the other AI tools that we're generating, the machine learning explainability is a lot easier because you're basically doing a fancy interpolation. It is what's happening. So kind of the explainability on the results coming out of these AI tools is something that is a future research issue. I know that there's a lot of research going on to give people comfort that the AI is in fact giving them the correct answer by being able to explain what the process was to develop that answer. Also, with the agents, there's a lot of using multiple different models to try to come to the same answer and making sure that all the models give you the same answer. But ultimately, explainability for a large language model gets difficult because the answer that you're asking for is the result of statistical next word guessing. So the algorithm that was used to generate the statistical most likely next word, you can prove out how that works and show how that works, but you can never be guaranteed that the answer is going to be correct. And again, so just asking the question of how many R's are in the word strawberry. Actually, let me do that. Let's see if it's going to give me a better answer today. So how many R's are in the word strawberry? So, oh my God, it worked today. literally last Thursday we did this, and it kept telling me 2. So kudos to the ChatGPT folks, because here you'll see that it, instead of just answer, actually, bear with me for 1 second. Let me go to instant and ask the same question instead of using the thinking model. Oh, it did come up with the right answer. And the reason that even the instant one is coming up with the right answer and why these tools are getting smarter is because this text interaction got fed back in as a part of the training set. So everything that you're asking the AI tools, I'm going a little, I realize I'm going a little bit off base of the question of explainability. And ultimately, with a large language model, you getting an explanation of how it came to the answer that it did is not going to be satisfying, because the answer is, if you say this word, and this word, I can do a statistical regression that shows that this word is the next one that will show up in the sequence statistically as the most likely word. What the algorithm is not doing is actually thinking about it. Now, in this case, there is a agent that says, okay, how would I explain to a human how to determine how many of a certain letter are in a word? And then it's going to use a large language model to create a set of steps. So list out each letter in the word individually, and then count how many times that thing appears. So, and as the tools get better, it's actually explaining what that work process is. So it's actually showing the answers to the individual questions that it's asking. But the whole explainability, I don't have the answer to it. And that's why right now we are reserving AI tools to be co-pilots and never drivers. So they're used to provide context to a human who's actually doing the thinking, as opposed to doing the thinking themselves. So the whole explainability is an area of active research. Kan Lee, a professor over at Purdue, I know is doing a lot of work on explainability. But unfortunately, I don't have a really good answer for you other than kind of explaining why it's so hard.
Okay, so let me take a very simple-minded view of this whole thing, and I interpret explainability as follows. If I ask a question, I'd like the answer, I get the answer. My vision of explainability says, okay, AI model, thank you very much for the answer. Now tell me why you got this answer. Okay, not how, but why. Okay, and it would come back and said, well, here are the 4 things that I found that relate directly to your answer, and here's why I concluded and gave you the answer I gave you. So that's my naive view of explainability. Did it make sense?
Yes. Well, let's ask it why it got the answer that it did. That's actually a pretty good explanation. But now the thing is, the why that it's giving you isn't actually telling you how it got its answer.
No, I don't need to know that. That's too complicated for my small brain.
Okay.
I just need to know why it got there. And since if I'm conversant in the field, that's enough for me to be able to say, okay, I think this is reasonable, or I see the limitations in what you gave me, and I'm going to go back and either do more work or beat you over the head to do it again for me.
Right. And that's kind of, another tip that I would just kind of go to with everyone out there that's using an AI tool is to ask questions like this. How did you get the answer that you got? Why didn't you come up with this answer? How could I have asked the question differently to get a better result? Asking those kinds of questions to large language models is going to help you become a better user of them. So why did you get the answer that you did is something that I've never done before, but now I'm going to do it more frequently.
Okay, thank you. I'm going to go off.
All right. Thanks, Doug. All right, Chris, what else do we have in the chat?
Let's see. We got one in here. It says, given that bulk of PSI information is going to be confidential for specific clients, how do you foresee training LLMs in terms of confidentiality of the data and getting better learning out of previous HAZOP projects?
Excellent question. So right now, the information that I've typed in, so what you're afraid of, and let me go back to my previous chat. So let's go to this P&ID to XML conversion. So right here, I input my entire schema. I input my piping and instrumentation diagram. How do I know that ChatGPT, that OpenAI is now not going to take my P&ID and make it part of the training set so that everybody in the world can ask questions about my P&ID because I put it into the system? Well, number one, there's got to be a lot of trust in terms of conditions of service. So what I know is that I am paying for ChatGPT. So I have a plus subscription, and I could go into my settings. Right here, you see this thing called Data Controls, Improve the Model for Everyone. I have it set to off. If you're not paying for the model, you can't set it to off. It's going to be improve the model for everyone and even include your voice translations. So if you have this set to on, which is the default when you're not paying for it, it's going to take the data that you put into the system and then use it as training data for future versions of ChatGPT. If you have it off, then the data that you put in does not get used for training. It's only used for your benefit, and you can at any point in time delete all that information, and it never gets used for training. I don't put anything super sensitive into here in the first place. Your other options are that you can use API calls to more trusted people. So I don't trust ChatGPT. I do trust Microsoft with a lot of our data. So all the API calls that are happening in our tool. So if I go to kiss.conexus.com, let me sign in with Microsoft, and let me make the screen a little bit bigger. So in the Conexus Integrated Safety Suite, I can click on this help button, and we already have a chat bot built into the Conexus Integrated Safety Suite that has training, or the vector database is the user manuals. So if I type in a question like, where do I input the beta factor for a SIL verification calculation, it's going to do that retrieval augmented generation. It's going to make a call to a large language model recursively. It's going to grab the information back from that recursive model, and it's going to present the results. So here it gave me an answer that said, this is where you put the information in. These are some typical numbers that you would use. This information is in the Vertigo user manual on pages 33 through 35, etc. So now when we generated this answer, we did what in AI terminology is called an inference. And that inference was done using Microsoft Azure AI Foundry, where we keep track of what are the questions, what are the answers that come back to us. Those API calls are not recorded in any way by Microsoft. Microsoft has no access to that information, and they can't do anything with it. So doing the inference with API calls with a trusted vendor gives you another level of comfort that your data isn't getting turned into a pure, that isn't being used as training for the base models. Now, if you are really, really security sensitive, there's no reason that you can't run the large language models on premises. So at your office, and this is something that we do have AI computers that are running inference models on premises here at Connexus. We're only doing it in research mode, but the whole reading of the data, the vector database, the returning of the information, you can run this on a computer in your building to where the data never leaves your building. Now, the computers that you're going to do this on, you're going to probably end up using lower quality models. It's going to run a lot slower, but it can be done. I mean, OpenAI, Google, they've got a lot more compute horsepower than the average company, but there's no reason that you can't do it on premises. So there are ways to keep your data safe. Item number one, pay money for your model. Go into your settings and make sure that they're not using the data that you provide to teach the base model is step number one. And then you could go all the way to running your inference on premise. Thank you for your time. Thank you for your attendance. Love doing these webinars. There will be another one next month.